This video is about a homework question. It's 7.2.015, Part B from the Larson and Edwards Calculus Early Transcendental Functions textbook, 7th edition. The problem statement says, find the volume of the solid generated by revolving the regions bounded by the graphs of the equations about the line y equals 7. I believe you also revolve it around a different line, but in Part B, we're revolving about y equals 7 in this case. So I would always start these problems by sketching the original region, and we sketch the region by just sketching these two equations. Now we know that y equals x squared is a parabola with its vertex at the origin. So in x equals 0, y equals 0. You don't have to draw a perfect graph. We're just trying to get a sense of what's going on. So that's one of my graphs. Now this is also a parabola, and I know it's a parabola because of the x squared, and I know it's a parabola facing down because of that minus sign. If the number in front of the x squared is negative, that means we've got a parabola facing down as opposed to up. Now to help me graph this, one thing that I like to do if you're dealing with a quadratic function that has two terms is just factor it. I'm going to factor out an x here. X times 4 gives me 4x, and x times negative x gives me that negative x squared. That makes it really easy to see what x values will give me a y equals 0. When x is 0, y is 0. And when x is 4, y is 0. So this is a parabola. Because of that -1, we know it's facing down, and it passes through 2 points on the x-axis. When x is 0, y is 0, so it crosses right here. And when x is 4, y is 0. So it's going to cross right here and right here. Now because of symmetry, because we know parabolas are symmetric about their line that goes through the vertex, I know that if my parabola passes through this point at 0 and this point at 4, that the vertex has to occur when x equals 2. The vertex has to be halfway in between 0 and 4, which would happen at x equals 2. So if I want to locate that vertex, I'll just substitute x equals 2 into this function. Say when x equals 2, y equals 4 times 2 minus 2 squared. So 8 minus 4. So y equals 4. That means our vertex for this parabola is at x equals 2, y equals 4. That's one way of finding the vertex. And x equals 2, y equals 4 also happens to be on the graph of y equals x squared. So it's that point right there, and we know we're dealing with a parabola facing down because of the coefficient of x squared. And so this is our region. You always want to start by graphing that region. We just did. So we're graphing the region. Oops, I'm so sorry. Graph the region bounded by the functions. Okay, so now we're here. And we're finding the volume of a solid of revolution generated by revolving this region about the line y equals 7. So after you've graphed the region, then we want to sketch y equals 7. And the reflection of the region about that axis. So our axis is up here at 7. So that's it right there, y equals 7. And I want to see exactly the same image over here, because if I'm taking this and I'm flipping it over that line y equals 7, I'm going to see that piece, it's going to appear over here. So let's just try to draw something that kind of looks like that. So symmetric with this 4, I'm going to have that 10 because 4 is 3 units from 7 and 10 is 3 units from 7. And then this point is 7 units from that line. So we're going to go all the way out to 14. 7, if we go 7 units that way, we'll go out to 14. So we're going to see something that looks like this. This curve gets reflected to be something like this curve. And it doesn't have to be perfect. It's just supposed to be that part of that parabola but flipped upside down. And then this curve, actually that's what I was just doing right there. And then this curve looks similar. We're going to see something that looks like that. Now I know it's not a great graph, but it's just supposed to give us the idea. So that's my original image, and that's the reflection, which isn't a very good reflection. Okay, now we're asked to find the volume of the solid generated by revolving this region about this axis. So we're going to have a solid that looks like this. Actually, in practice, it would probably look kind of a weird, bowl shape. This is what we would see. I always try to visualize what the solid will look like when we're done. But if we looked inside the bowl, it would have like a bottom cut out of it. So it wouldn't be a very good bowl at all. And what we would see is edges that are kind of sloped in like this. I hope that helps. If it doesn't help, it's okay. We can still do the math and find the volume of the solid, even if we can't visualize that solid very well. Okay, so we've graphed the region bounded by the functions. We sketched the reflection about the axis. And the next thing we want to do is slice this solid perpendicular to the axis. Now you also have the option of slicing the solid parallel to the axis. You could use the cylindrical shell method, but since we're in 7.2, the expectation is at this point that you only know the disc and washer methods. So we'll use the disc or washer method here. Okay, so I'm going to slice, since I'm using this disc or washer method, I'm going to slice perpendicular to the axis. I'm going to slice it like you're slicing a loaf of bread, perpendicular to that axis. So we'll do that. And remember, we do that anytime we use the disc or washer methods. And my representative slice is going to look like this. Okay. Looks like Salvador Dali made it. Salvador Dali slice. Okay, so I've got this slice. It's a washer. Hopefully you can see it's a washer. After we have sliced parallel to the axis, and then we sketch a representative disc or washer. Then you're going to choose. You're going to ask yourself whether it's a disc or a washer. Then you're going to ask yourself whether we should have a delta x or delta y integral. So I look at this slice and I think I can see that it's a washer. Now, if you're not sure whether the slice should be a disc or a washer, this is how I always do it. Look at your axis and look at the relationship between that axis and the region that you started with. If there is a gap between your region, so it's this pink region, and the axis, then you're going to have a washer. Now, if this region were to sort of butt up against that axis, so maybe the region would actually go all the way up to that line, well, then that would be a disc. But we don't have that. We're not in that situation. We've got a gap, so that means we're going to use the washer method. The inner radius starts at the axis, and it goes down to that top curve there, it's the inner radius of our washer. And then the outer radius starts at the axis and goes to the outer edge of that disc. That's the outer radius. So this is little r, and that's big R. And then I also want to decide, we've got a washer there because of the gap. I also want to decide whether it's a delta x or a delta y integral. Since this little width or thickness of that washer is a tiny distance in the x direction, we're going to integrate with respect to x rather than y. So we've got that right there. All right, so we know we're using the washer method, we know we're integrating with respect to x. So now we want to find the formula for the volume of the ith washer. And we're assuming that we've got n washers. So we've subdivided our solid into n little washers. And we just want to find the volume of a representative one, which we're calling the ith one. Okay, so the volume of that washer is the area of one face of a washer times the thickness. The area of a face is just the area of the larger circle minus the area of the smaller circle. If my large radius is called capital R sub I and my smaller radius is called lowercase r sub I, that's my area, large circle area minus small circle area, and then we're multiplying by that little thickness or width of the disk, and that's delta x because it's a tiny distance in the x direction. Factor out the pi, and now we've got this. Okay, so now I need the radius, or the inner radius and outer radius entirely in terms of x. So that's our next goal. In order to find this volume, we state the correct formula. And then we find both the inner radius and the outer radius. Okay, so look at my picture. And I say to myself, okay, the radii are both vertical. So we're going to use, anytime we have a vertical distance, the top y value minus the bottom y value. But we're going to do this in terms of x because of that dx over here. So the top y value as a function of x, well, it just happens to be y equals 7. Doesn't explicitly depend on x. And then the bottom y value is given by the y value on this curve because that's the one that goes out to that outer edge. The outer edge of the disk is right there. Or excuse me, the washer is right there. So the bottom y value is just y, but in terms of x, if I'm on this curve, y is equal to x squared. Remember, they gave us that at the beginning. So I'll subtract x squared from this, and I'll call it x sub I squared because I'm talking about the ith x value. It's on that ith subinterval. Okay, so that's what we do for the outer radius. The inner radius is also vertical. So we have the top y value minus the bottom y value. And the top y value is still 7, that hasn't changed. And the bottom y value is still a y value on a curve, but it's not on this curve, it's on this curve. So I want the y value on this curve now in terms of x. Oops, sorry. I tried to toss that pink highlighter in the trash and it made kind of a ruckus. The y value on that curve in terms of x is that 4x minus x squared. And again, that was given to us. And don't forget your parentheses. You need to distribute that negative. So you've got 4x minus x squared. We're talking about the I disk, so we'll put in a little I on there. All right, so now we've got the inner and outer radii, and we want to substitute those into our formula. So the volume is pi times the outer radius squared minus the inner radius squared times delta y. The outer radius is 7 minus x sub I squared. The inner radius is this. I think I'll just distribute that negative right now. We'll have 7 minus 4x minus a minus is plus x squared. And we need little eyes on that. And the total volume is approximated by the sum of all of those volumes, the volume of each of those washers. We assume we've got n of them. And we can write that shorthand using Greek, our sigma notation. So that's that. Now if I wanted to set up a Riemann sum, this is a very specific case of a Riemann sum, I would substitute that right here. You see what mistake I made? That should be a delta x, not a delta y. I hope you caught that when you were watching the video. If you did, that's a good sign because those variables should match. If they don't match, we did something wrong. And let's look at our picture. Yep, it's still delta x. I just wrote the wrong thing down over here. Okay, so if I'm setting up a Riemann sum, or what's a very special case of a finite sum representing this volume, it's a finite sum. I would put this right in front of the sigma. Okay, so if I want the volume, I take the limit of that as the number of washers goes to infinity, or if you prefer, as delta x approaches 0. And that will be equal to the limit, well, it's obviously equal to the limit. That will be equal to the definite integral. And we'll write that down in just a second. I think I drank too much caffeine or something. Making a lot of little mistakes. Okay. So let's factor out the pi. Got 7 minus x squared quantity squared minus the quantity, 7 minus 4x plus x squared quantity squared. We're integrating with respect to x. Now we're not done yet. We need limits of integration right here. To find the appropriate limits of integration, we always want to go back to our picture and then look at the original region. The question is, where does x start and stop since we're integrating with respect to x? Now, hopefully you remember when we sketched this, we saw that they both cross here at x equals 0, and they also intersect, those two parabolas intersect at x equals 2. So we're going to integrate from 0 to 2. And that is it. That's the setup. Now, if I want to integrate this, I've got to do a little bit of algebra, and then it's just a bunch of power rules. So it's not too bad from here. Let's do that on the next page. Volume is pi times the integral from 0 to 2 of 7 minus x squared quantity squared minus 7 minus 4x plus x squared quantity squared. For each of those guys, you might want to write them twice in FOIL. Or for this one, we can't really FOIL. I guess we're just going to distribute. And if you want, you don't have to do this in line inside the integral. You can do the algebra outside the integral and then substitute it back in. That'd be just fine. Just remember what you're doing. Keep track of all of those steps. So eventually you substitute it back in and to integrate it from 0 to 2. Okay. Here, when I FOIL, first times first is going to give me 49. Outer times outer is negative 7x squared. Inner times inner is just like it. So we get negative 14x squared. Last times last, that's a negative times a negative. That's a positive x to the 4th. Now over here, it's a little bit more challenging. Not because it's difficult, just because it's a little longer. What we're going to do is we're going to take each of these guys, we're going to multiply it by the whole thing over here. So I'm going to say -7, and I'll distribute that negative at the same time. -7 times this quantity. That's how we distribute. So we're doing 7 times all of that. And then we're doing -4x times a -1 is +4x. That times all of that. Again, negative times negative is a positive. And then the last thing we do is -1 times x squared times all of that. Dx. Still a lot more algebra to do. Not much calculus here. That's okay. It's a little bit of a mental break from calculus. Something nice and easy. Something familiar. Distribute the -7. We get -49, +28x, -7x squared. Those reduce. Distribute the 4x. We get 28x, +4x times -4x is -16x squared. 4x times x squared is 4x cubed. And then over here, I get -7x squared plus 4x cubed minus x to the 4th. And I'm sorry I'm writing so small. I was just running out of space. I'm sure that that's happened to you before. Okay, so we're almost done. We just have to simplify this. So let's collect like terms. Looks like the highest power of x we've got is x to the 4th. I like to put the highest power of x first, just because I'm a math teacher. I bet we're just in the habit of doing that. I've got an x to the 4th here and a -x to the 4th there, so they actually reduce. Is that it? Yep, I think those are the only x to the 4ths. And now we want to do x cubed. There's one, and there's another one, 4x cubed plus 4x cubed. That's 8x cubed. Okay, now let's do the x squared. I've got -14x squared minus 7x squared, that's -21x squared, minus 16x squared, -21 minus 16 is -37x squared. And I forgot that -7x squared, minus another 7x squared. And we'll collect those like terms in a minute. And then let's see, we need the x terms. I've got a 28x and a 28x. And so that is 56x. And I think that's all we've got. Let's make sure, didn't miss anything. Okay. And of course, we can combine these terms. That's -44x squared. And it's just the power rule from here. So bring your pi down, bring your 8 down, add 1 to the exponent and divide by the new exponent. Bring your constant down, add 1 to the exponent, divide by the new exponent. Bring your constant down, there's an implied 1 there. Add 1 to the exponent and divide by the new exponent. Substitute in 0 and 2 and subtract. And you can simplify if you want to. Okay. 4 goes into 8 twice. 2 goes into 56, 28 times. So we're going to have pi times 2 to the 4th minus 44/3 times 2 cubed plus 28 times 2 squared. And if we substitute x equals 0, we're going to get 0 minus a constant times 0 plus a constant times 0. So we're just going to get a bunch of zeros there. So this is our answer. It's just not simplified. I trust that you can do this arithmetic order of operations problem if you're in Calculus 2. So we will use the calculator for arithmetic, not because we don't like it, but because we don't want to waste time in the video teaching you how to add fractions. So I get 80 over 3 times pi. Don't forget that pi, and that's units cubed, because remember we're talking about volume, and if you're saying volume of what? It's volume of this. If you take this little piece and you revolve it around, what you're gonna see is you're gonna see that other piece over here. From the outside, it's gonna look like a bowl. You kind of look like this. But if you look inside the bowl, you're gonna see it's not a very good bowl. It has this bottom piece cut out, and it actually has these edges that are like angled like that. If you were to look inside, maybe it looks like a horn, like if you can imagine that, like a horn inside. But that's what the volume of that is. It's 80 pi over 3 units cubed.